So the eccentricity of a vertex, or sometimes it's called the covering radius, is the maximum distance of view of a vertex in X. And the maximum value, just for reference, the maximum value of the eccentricity over all the vertices would be the diameter of the graph, but we don't really care about that. Now, in the last lecture, I proved that the diameter plus 1 was a lower bound on the number of distinct eigenvalues of the graph. And so I'm going to prove an analog of this. I'm going to prove that the eccentricity of vertex plus 1 is a lower bound on the size of the eigenvalue support of that vertex. Okay, so the proof is very similar. So if the eccentricity of vertex is k, then we look at the vectors a plus I to the r times e sub u. Now the I is in there because of problems you run into with bipartite graphs, but a to the I r plus u is a vector, and its support, the set of values in which it's non-zero, increases strictly as you go from 0 to k. Okay, because when you go to k minus 1, there are no vertices of degree k, and no vertices of distance k from u in the support. So these k plus 1 vectors, their supports is a strictly increasing sequence. And so the conclusion is that those vectors are really independent. Okay, so that's the same as before. But these k plus 1 vectors lie in the span of the eigenvectors, span of projections of E sub u onto the eigenspaces. Okay, and the number of those vectors is this size of the eigenvalue support. And so we get that k plus 1 is bounded above by the size of the eigenvalue support. And so the conclusion is that the size of the eigenvalue support, that is at most, does that make sense? Well, it's equal to it. Excuse me. Which way do you want it? The eccentricity plus 1 is bounded. Yeah, okay. We can make significant use of that. So what's going to happen is if the eigenvalue support is not large, then most of the vertex is small, and most vertices in the graph are close to that vertex. Okay, and so that means if the graph is k regular and the eigenvalue support is not big, that the number of vertices of the graph is something k to the eccentricity or k to the twice eccentricity, doesn't matter, but it's going to bound the size of the graph. Okay, so that's what's going to happen. Now, we're not going to do that for a little while yet, but that's where we're going to use it. So it's going to give us, enable us to prove that there's only finitely many connected graphs with maximum boundary k admitting perfect state transfer. Okay, so as a side remark, if the graph is vertex transitive, then the eigenvalue of the support of the vertex is the spectrum of X. I don't know whether to explain this or dump it on you as an exercise. It's a good exercise. Let me think about this for a second. I'm going to make this an exercise. Leave it at that. But anyway, this is a fact we can use if we need it, that the eigenvalue support of a vertex is just the entire spectrum. Okay, so that's what I wanted to say about the relation between the eigenvalue support and eccentricity. I need to talk about cospectral and non-cospectral vertices, because these are properties shared by vertices involved in perfect state transfer. Now, then the first claim is if X emits perfect state transfer from a vertex A to a vertex B, then A and B are cospectral. Now, I don't know why I've written this down as an exercise since I've given you so this is the assumption that we have perfect state transfer from A to B at time t. Actually, yeah, it was in an exercise. There was an exercise with a different proof. Not sure. Anyway, if I multiply this by a to the m on both sides. Now, a to the m commutes with ut. Okay, so if I do that by on the right and left by a to the m, then the left side becomes this, and the right side just becomes this. Now, this is just the outer product of the vector a to the mb. And so the trace of this is the sum of the entries in a to mb, which will be a number of walks of length m starting at b. And on the other side, you've got the number of walks of, yeah, this is why it's not complete. So, and okay, and that is, C, which is, yeah, and okay, that's what I'm missing. U of t is a unit operation, so the vector AMA and the vector UT AME sub A have the same norm. Okay, and so since U of t doesn't change the norm of this vector is just the norm of A to the ME sub A, and that's the number of walks of length M starting at A. So that's, yeah, there is an exercise to be done there. This is just, you want closed forks in there at some point. But my advice is to take traces. The other point is that, well, this is the way they use, if vertices A and B are co-spectral, then we have that ER AA equals ER BB, but this is equal to EA transpose ER EA. And this is in turn equal to E to the A transpose, because we're dealing with an idempotent and because they're symmetric. And similarly, this is E. And so this tells us that if the diagonal entries between the A and B and the idempotent are equal, then the vectors E to the R, EA, and E to the R, EB have the same norm. That's what that says. So that's equivalent. That will come up before too long. Okay, so the reason I'm not trusting too much about the fact that if I get transferred from A to B, then A and B are co-spectral is because something stronger is true, and that's what we'll work with. But this already tells you, if they're co-spectral, it tells you that vertices A and B must have the same valency. In fact, the walk generating functions at A and B must be equal. But as I said, something stronger is true, and that's where we're going to go next. Now, before we get onto that, though, so what about examples of co-spectral vertices? Well, you've seen some. I talked about similar and pseudo-similar vertices and things. But any two vertices in a strongly regular graph are co-spectral. Okay. Now, we saw that if X is strongly regular, then it's equivalent to the definition that A squared can be written as K times I, K is the valency, plus A times A, where A is the number of triangles on an edge, the number of common neighbors of two adjacent vertices. And if two vertices are a distance 2, then they have exactly C common neighbors. And I can rearrange this and write it as any combination of I, A, and J. Now, it then follows by induction that for any integer, non-negative integer M, A to the M is a linear combination of I, J, and A. I mean, if I multiply this by A, I get an A times J, which is going to be a constant times J, and an A squared, but A squared is a combination of I, A, and J. So it's a straightforward induction. We get that this is true. And so this implies that then any polynomial A has constant diagonal. If the diagonal of I is all ones, the diagonal of J is all ones, the diagonal of A is 0. So strongly regular graph, each vertex is walk regular. Each vertex is yeah. So so that the diagonal entries of A to the K are all equal for any K, and therefore any two vertices are cospectral. Okay, so this might suggest, gives you grounds to hope that strongly regular graphs would give you lots of examples of perfect state transfer. It doesn't, as we'll see shortly. Want to bring in some jargon. So we say a graph is walk regular if all vertices are cospectral. Now you can think of this as a generalization, a linear algebra generalization of being vertex transitive. Because certainly vertex transitive graphs are walk regular. Okay, and strongly regular graphs are walk regular, as we've just seen. And complements of strongly regular walk regular graphs are walk regular. You only run into trouble if you try and prove that using the generating functions. Finally, any of the standard graph theory products, in particular the direct product and the Cartesian product of walk regular graphs are walk regular. Now, the significance of that is I can take two different strongly regular graphs, different parameters, take their direct product or the Cartesian product, I get a new graph, which is still walk regular, but it's no longer strongly regular or anything like that. So you can get lots of graphs that walk regular, but using products to mix things up. I mean, there are also other products, lexicographic products and strong products, and the same result holds there, but it's just some. And these will be in the exercises. Well, funny. What about a claim then? Excuse me. And now it looks like a theorem. So I want to prove the graph is walk regular, and it's got at least three vertices and has most n on two simple eigenvalues. Now the complete graph on two vertices is walk regular, and it has two simple eigenvalues. So I need that condition that the vertices is greater than or equal to 3. Now I want the proof in a certain sense doesn't use anything complicated, but the details are a little tricky, which is probably bad news. So the strategy first will show that if Z is an eigenvector with simple eigenvalue lambda and K is the valency of X, then you may assume that Z is a plus minus 1 vector and that K minus lambda is even. Now, this is a bit surprising. It's not clear what use this is, but we'll get to that. So that's the first step. So we're going to prove that a simple eigenvector, so to say, is a plus minus 1 vector. Okay. Now the next thing, well, by virtue of this fact, in fact, the simple eigenvalues of X lie in the interval K minus 2, K minus 4 down to minus K. This is a consequence of that. Okay. And so the number of simple eigenvalues is at most K. Okay, that's straightforward. Second thing is that the simple eigen, if you look at the complement, now the general rule is that the eigenvalue is if theta is an eigenvalue of X, then minus 1 minus theta is an eigenvalue of the complement. Except for the valency, it goes from K to n minus 1 minus K. And this is for regular graphs. There's no simple expression for the spectrum of the complement of a general graph, but for regular graphs, we have this relation. I'm not saying there are no relations between the eigenvalues. I'm just saying they're not simple and there's no formulas. But if the graph is regular, valency K. You have to pay a little bit of attention when the graph is not connected, but I'm going to roll out details in a moment. But the general principle is that the eigenvalue of the graph is theta, then the eigenvalue of the complement is minus theta minus 1. This is simply because the eigenvectors of a regular graph, well, you have the valency, and so the all-ones vector is an eigenvector with that valency, and you can assume that the other eigenvectors are orthogonal to that. Okay, so they're orthogonal to J in particular. And so from that, you get this relation that the theta in the graph goes to minus theta minus 1 in the graph. Now, if we've seen that the simple eigenvalues is the most k, and you go to the complement, you get the number of simple eigenvalues is the most n minus k. And so now you've got s less than or equal to k plus, and so there should be a k plus 1 in there somewhere. I think this is n minus k plus 1. And so 2s is less than n minus 1. Now, we're going to see the n is even, and so this proves the theorem. Now, the first version of this was simply Petersdorf proved that if you had a vertex transitive graph, then the eigenvalues couldn't all be simple. Okay, and so what we're doing here is we're extending it to walk regular graphs. Okay, which are a significant generalization of vertex transitive graphs, and we're getting a sharper form. Now, this results in some interest in itself, but we'll also be using it later on when we come to strongly co-spectral vertices. So now I want to go to the proofs. So I remind you again, there are the 3 steps. We're going to first get the structure of the eigenvector. Then we're going to prove that the simple eigenvalues of x lie in this range, and then ditto for the complement. Okay, and so let's head to that. So we assume our graph's got n vertices as usual. Now, if x is not connected, then each component is walk regular. Now, you need to think about that a little bit. See, if a graph is vertex transitive, then each component is vertex transitive. And there's an easy sort of group theory argument for that, but we're not assuming that. We're assuming that we're walk regular. And so the point is we're saying walk regular. So we're saying that x drop A and x drop B have the same characteristic polynomial. And so from that you can see, and from that you can deduce that each component of x is walk regular. Okay. And in that case, since x drop A and x drop B, if A and B are in different components, x drop A and x drop B are still co-spectral. And so it follows from that x has no simple eigenvalues. Now I've put a y there, so you should go off and think about that. But so the point is, if it's not connected, then it has no simple eigenvalues, and so we're done. So we're going to assume x is connected with velocity k, and we know that k is simple because the graph's connected, and so we saw that a long time ago. Now let lambda be a simple eigenvalue not equal to k with eigenvector z. Then the idempotent d lambda is a non-zero scalar multiple of ZZ transpose. Okay, if an eigenspace is one-dimensional and Z is an eigenvector in space, then ZZ transpose is a scalar multiple of the projection. And if Z is a unit vector, then ZZ transpose is the projection onto that subspace. Okay, so the idempotent is a non-zero scalar multiple of Z transpose. Now, the thing to notice now is that, well, E lambda is a polynomial A, and so E lambda has constant diagonal. Okay, and if it has constant diagonal, then, well, definitely ZZ transpose has constant diagonal. Now, what are the diagonal entries of ZZ transpose? They're the squares of the entries of Z. So all entries of Z have the same square. Okay, and since we're dealing with a real vector, that means the entries of Z are all 1 and minus 1. And as Z must be orthogonal to the all ones vector, there must be an equal number of 1s and minus 1s. So we've proved that Z is a plus minus 1 vector and n is even. Okay. Now so that's the taking care of the structure of the eigenvector. Now the eigenvalue, what do you say about that? Well, we look at our basic equation. So we have lambda ZA is equal to the sum. If Z is an eigenvector for A with eigenvalue lambda, then lambda ZA is equal to the sum of the values of Z on the neighbors of A. Now, this is a sum of ones and minus ones. And so the number of terms in the sum is congruent to the valency mod 2, since A is a k-regular graph. And so that tells you that k minus lambda is even. So we've learned that n is even, that if lambda is a simple eigenvalue, k minus lambda is even, and that a simple eigenvector has entries 1 and minus 1 with equal number of each version. So that's the first step. Now, the rest is more straightforward. Assuming x has got exactly s simple eigenvalues, and we're assuming the eigenvalues of x are given by this. And so I'm writing out all the eigenvalues, not just the distinct ones. So then the eigenvalues of x bar are given by this. Now there's again a minor hiccup. If x bar is walk regular, I told you that before, but it's your problem. And if it's not connected, there's no simple eigenvalues. And so we can assume, might do a lot of fiddling, that x bar is connected. Okay, and so that means that this is a simple eigenvalue. Okay, and so we're in exactly the same situation we were before, except now instead of k, we've got n minus 1 minus k. Now we saw that s was at most, now I mean it's k plus 1, yeah. Yeah, so s is at most k plus 1, okay, but this. And on the other hand, going to the complement, you get that s, the number of simple eigenvalues is at most n minus 1 minus k plus 1. So we get these two equations, and you sum those, we get 2s less than n plus 1. And so then the result follows. Now, so a walk regular graph can't have too many simple eigenvalues. I guess it could always be fun to construct examples where they bounce type, but I haven't tried to do that. So that's it for cospectral. Now, I'm going to introduce a stronger definition. I'm going to say two vertices of graph are strongly cospectral if the projection of EB onto the R eigenspace is plus or minus the projection of little e sub A. So the two vectors are either equal or of opposite sign. Now, if this is true, then these two vectors have the same norm. So vertices A and B are cospectral. So as you would hope, strongly cospectral implies cospectral. Okay, we'll see that the converse is not true, far from it. Okay. The other remark is if the eigenvalues of your graph are simple, then cospectral vertices are strongly cospectral. Now, how do you prove this? If an eigenvalue is simple, then ER EB and EA are both eigenvectors with the same. No, get this right. I claim as if they're simple. Yeah. Well, the eigenvalues are simple. If the vertices are cospectral, then the vertices indexed by A have the same square. Okay. And yeah, so because no, just think if we're simple. Let's okay, let me give myself a page and actually do it. So we've got vectors, assuming X's eigenvalues are simple, and oops, A and B are cospectral. Now let's look at EA and EB. Now both these guys are because if they're co-spectral, then the A entry of ER-EA is equal to the B entry of ER-EB. And so if one is not zero, the other is not zero. And since they're eigenvectors, okay, so they're non-zero. Now, this vector is plus or minus this vector because we're, well, no, we're not assuming they're co-spectral. Now, these belong to the same eigenvalue. So this must be equal to a scalar times ER-EB. Both eigenvectors with the same eigenvalue. Okay. So but the other point is that they're co-spectral, so they've got the norm of ER-EA is equal to them. But because so that implies gamma is equal to 1. Now everything is real here, so that implies gamma is equal to plus or minus 1. Okay, so if the eigenvalues are simple, then co-spectral vertices are strongly co-spectral. Now, just to give an example of a graph with strongly co-spectral, with simple eigenvalues, take the path. Now, first thing is, suppose we have an eigenvalue theta, which is not simple. Then I can find two eigenvectors. Well, I claim I can find an eigenvector for the graph, which is 0 on the first vertex. Because basically what I do is I pick two eigenvectors. Either one of them is 0 on the first vertex, or that they both equal to some non-zero constant, but then I can take a multiple of one away from the other and get a second eigenvector or third eigenvector, which is now 0 on the first vertex. So if the path has an eigenvalue multiplicity greater than 1, then it has an eigenvector which is 0 on the first vector. And now you see me do this diagram tracing. So we've got the eigenvector is 0 and 1. And so now theta times 0 must be the sum of the weights of its neighbors. And so this must be 0. And so it turtles all the way down. So this tells you that the eigenvalues of the path are simple. Okay. And so, and these two vertices are certainly co-spectral, so they're strongly co-spectral. The two vertices in Schwenk's magic tree are co-spectral, and the eigenvalues of that graph are simple, so they're strongly co-spectral. So we have some examples. Okay. Any questions at this point? Yes.
So you're assuming in the thing exercise, you're assuming they're being parallel, or
I was trying to avoid mentioning that.
because they're coefficients and.
Well, I'm proving they're parallel, aren't I? I'm not assuming it.
The eigenvalues are simple, so they are parallel.
Okay.
Yes. Yes. Okay. Yeah. So the point is that that's exactly what this statement's saying.
Okay. Thank you.
Yeah. Yeah. In the notes, you'll see a discussion that we talk about parallel vectors, and I have a feeling that I can get through what we need without mentioning the word parallel. And the fewer terms we introduce, the happier everybody is. But in the notes, two vectors are parallel if one is a scalar multiple times the other. I think the zero vector is probably parallel to everything, but it doesn't matter too much. So two vectors are parallel, and so we can split strongly co-spectrality into two conditions, but I'm not going to do that because I don't need to. So we've seen, I've got some examples. I said there are a number of constructions in the corresponding chapter of the text for co-spectral, for strongly co-spectral vertices, but I won't go into that now. So that's all I'm saying. There are other constructions given the notes. Now, the reason that strong co-spectrality is relevant is, well, I said that if two vertices are related by, if there's PSD from A to B, vertex A to vertex B, then A and B are co-spectral, but I said wasn't too worried about the proof of that because a stronger condition is true. They're strongly co-spectral. So let's suppose we have PSD from A to B. There it is at time tau. Then this is now a product of EB with itself, and this is now a product of U tau EA with itself. And so, well, to use the language we just brought up, that means EB is parallel to U transpose EA. This is some complex scalar. Now, U of T is unitary, So this vector has length 1, just for the sake of reminding you. And then, okay, so I get this equation by pulling apart the outer products. Okay, and then I get that I apply ER to both sides. Now, I get EREB. Now, U of tau applied to ER is just the eigenvalue of U of tau belonging to theta R. And so you get this. I mean, ER, the columns of ER are eigenvectors for U of tau with eigenvalue e to the I tau theta R. So we get this equation. Now, again, since this has norm 1, oops, and this is a complex number of norm 1, and this is a complex number of norm 1, it follows that gamma has got norm 1. And so in particular, this has norm 1. And so, okay, but these vectors are real. Okay, so this is real and this is real. So this must be real. And so that means this is plus or minus 1. Okay, so that gives you the strong ecospectral. Now, the sign matters. And if you try to actually write out explicit characterizations of the existence of post-state transfer, then you have to pay attention to those signs. I'm hoping to avoid that. I don't, so we'll leave it at that for now. I mean, there are details and notes, but the point here is that if two vertices in perfect state transfer, they're strongly ecospectral. Okay. And the obvious place, we saw that any two vertices in a strongly regular graph are cospectral. So the obvious place to look for strongly cospectral vertices is in a strongly regular graph. Well, that's a bad idea. If any two vertices in a strongly regular graph are strongly cospectral, then the number of vertices is at most 2. So, so if we assume any two vertices are strongly cospectral, then for each eigenvalue theta r, the projection E sub r applied to the basis vector E sub r spans the theta r eigenspace. Okay. Now, because if it's some other vertex B, any ER times EB is plus or minus this. So this vector by itself spans the ER eigenspace. So all eigenspaces are one-dimensional. So all eigenvalues are simple. And as X is regular by what we just proved before, number of vertices of X are most 2. Now this doesn't prove that a strongly graph can't have strongly cospectral vertices, but that's actually true. But to prove that, I have to fiddle a bit more with the theory of strongly graphs than I want to at this point. Now, what I want to offer next is a characterization of when two vertices are strongly cospectral. Now, this is an example where we're going to construct something. We've got two vertices A and B are strongly cospectral. We're going to construct an orthogonal mapping, which is trying as hard as it can be to be a permutation matrix, but not quite making it. Okay, so two vertices of graph are strongly cospectral if and if there's an orthogonal matrix Q. It's a polynomial A, and its entries are rational. It maps A to B, and its square is the identity. And now if it maps A to B and its square is identity, of course, it also maps B to A, so it swaps A and B. So, you know, well, who knows about polynomial A? If a matrix has only simple eigenvalues, then anything which commutes with it is a polynomial that matrix, but that's another story. But the point is, it's rational. Well, permutation matrices are rational. It's sending A to B, that's what permutations do. And the square is identity. Well, it's easy to write down permutations like that. So it's trying very hard to be an automorphism. Now, of course, in general, it is not true. There won't be an automorphism. Okay, we can find graphs that with no non-trivial automorphisms with pairs of cospectral vertices. And in fact, the first example would be Schwenk's tree. Let's see if I can. 1, 2, 3, 4. And I think it's this and this. So that's Schwenk's tree, and those two vertices are co-spectral. The eigenvalues are simple, which you can check in various ways, putting in sage, for example. So they're strongly co-spectral, but clearly no automorphism in the graph maps this to this. Now, you can also use this result to prove that a strongly regular graph can't have a pair of strongly co-spectral vertices, because in that case, Q is a polynomial in A, and so this condition forces Q to look like 0, 1, 1, 0 all the way down. But I don't need that, so I won't go there. So we're claiming all this is true. Okay. So, well, we start with the spectral decomposition of A, and we've got two, and we've got our two vertices A and B that are strongly co-spectral. Then there are scalars sigma r taking values plus or minus 1. Oops. Taking values plus or minus 1, such that ER, the projection of little EB is plus or minus the projection of little EA. Okay, so we've got these scalars sigma r, one for each eigenvalue. So, and such that, well, so you want this to hold if only if I've got too many subsets there. So we've got these scalars, and I can define a polynomial P of T, which takes value sigma r on theta r. And what I'm saying is that we need, or what we want, is PA. We want this polynomial in A applied to A to give us EB. Now, why do you want that? Well, PA applied to EA is this by spectral decomposition applied to EA. Now, EREA, P theta, P of theta is sigma r, and sigma r of EREA is ER of EB, and this sum is over R, but B is constant, and the sum of the idempotents is the identity, so CB. So if I can find this polynomial, well, you can, of course, then I can get P of A doing this. I have to fix this up on me. Make myself a scrappy note here. Just remind me to fix it in the notes. So now we have to compute PA squared. Well, PA is sigma P theta R. Yeah, that's just the spectral decomposition. Or okay, and when you square it, the ER times ES is 0, so you're only going to get the diagonal terms ER squared, but ER is idempotent, so ER squared is equal to ER, and sigma R squared is equal to 1, and so you get that PA squared is equal to I. And so we can define Q, whoops, I don't really want to do that, to be, I can define Q to be P of A. So I have a matrix which swaps A and B. Well, I haven't checked that, but you can check that. And has order equal identity, and it's a polynomial in A because it's a linear combination of the idempotents of A. So the only thing I haven't done is proved it's rational. Now, I'm not sure we'll ever need this, and you probably won't enjoy it. You can view this as a warm-up to what comes next, because to work with the continuous quantum works and try and work out when you get perfect state transfer, we need to use some non-trivial number theory to restrict the eigenvalues. Okay, and so you can view this as something of a practice run. So my problem is to show that this matrix Q is rational. Now, the way it's defined, it's just a signed sum of the idempotents of A. Okay, now the entries, the eigenvalues of A are so-called algebraic integers, and so the entries of the idempotents are so-called algebraic numbers. Okay, so they satisfy a polynomial with integer coefficients. So there's, you know something about them. It may not help you much at this stage of your career, but you do know something about them. So the what I'm going to do is I'm going to take the extension of that should be the rationals and make it. It's unfortunate. Like a little cube. the extension of the rationals generated by the eigenvalues of x. So that's the smallest field that contains the rationals and the eigenvalues of our graph or our adjacency matrix. So we've defined second field. And we're going to choose an automorphism alpha in the field. Now that alpha must fix the rationals. In fact, alpha is the rationals are precisely what it fixes. We'll come back to that. But if alpha is one of these field automorphisms and theta is an eigenvalue, and you apply it, then it maps the minimal polynomial of theta to itself because the coefficients of the minimal polynomial are integers. So when you apply the field automorphism to that polynomial, the only thing that changes is theta. So the point then is that the alpha fixes the polynomial, and this implies that it permutes the this implies that it permutes the zeros of that polynomial. I mean, you've got t minus 0,1, t minus 0,2. The only thing that alpha can do to reserve it when it acts on the field entries is permute them. So it permutes the entries of the minimal polynomial, and from that, it follows that phi permutes the eigenvalues of the graph. Because it does this for any minimal polynomial of any of the roots, so that so phi just permutes the eigenvalues in orbits in some fashion. Now, so we have alpha. Where's phi come from? We have alpha. It's permuting the eigenvalues of our graphs, and we can apply it to the spectral idempotence just by applying it entryways. And I get a matrix which I'll call EDR super alpha. Now, the thing to notice is that if we apply A to EDR theta alpha, since A is an integer matrix, A to the sigma is equal to sigma, that should be an alpha. Yeah, just like I think you're going to get a mixture of sigmas and alphas from this point on. So since A is an integer matrix, it's fixed by our alpha, and so I can pull it in. Now A applied to E sub r is theta r E sub r, and then this should be an alpha there. So this tells us that each column of E sub r to the alpha is an eigenvector for A with eigenvalue theta r. And so that's telling you that, giving me another proof, if you like, that theta r to the alpha is an eigenvalue of A. So each field automorphism is permuting these eigenvalues around, and in particular, that EDI alpha is a spectral idempotent of A with eigenvalue theta r to the alpha. Now, since it's an idempotent, the diagonal entries is probably semi-definite, and the diagonal entries are non-zero. Okay, so the problem to be careful at here is that alpha can change. It can map an eigenvalue theta to minus theta, so it can change signs. It can't change signs of integers, but it can change signs. So if your eigenvalue is √2, there's a field automorphism which sends √2 to minus √2. So signs can change. So you've got to be a little bit careful sometimes, but that's not going to happen here. Now, okay, so yeah, fine. This sigma here is the sigma I was defining using earlier when I defined Q. So I'm still in the same proof, so that's all right. Now, so the point about is that the AB entry of EDR is plus or minus the AA entry of EDR. Now, yeah. And so the conclusion then is that the AB entries of these two matrices have the same sign. And so the conclusion I get from that is that this sum, these are the signs, is fixed by alpha. And then that means that in fact it's fixed by any field automorphism. And then we have to use the fact that since the field that we constructed with the smallest field that contains all the eigenvalues is a splitting field, the only things which are fixed by all field automorphisms are rationals. So in general, if you've got a field F and an extension E, the field elements fixed by automorphism V may contain things that aren't in F. But if you're constructing it from as a splitting field as the field containing all the eigenvalues, then that's not a problem. Now, I don't expect you to know that. There's a slight chance you've ever taken a course of Go-I theory, you've seen it. But my point is so the point is we're using some non-trivial Go-I theory at this point. Now, I'm not going to expect you to write down any proofs involving Go-I theory, but you do need to see that we're using it, okay? And so the factor we're using here is that, so I take my field rationals, I take the smallest field that contains the rationals of my eigenvalues, and I look at a field automorphism, and then I argue that field automorphism must fix Q. And then I bring in the heavy gun, then I say that because there's a splitting field, any field automorphism which fixes any element of the field which is fixed by each field automorphism must be rational. And we'll be using that again. Now, as I said, I don't expect you to know that, and I doubt that I could write down a proof without a lot of warning. Okay, but it is, standard Go-I theory, and this last fact I'm talking about is actually quite useful. So we will be using it again. So as I said, you can view this more as a threat. We're going to be having to deal with some of these things, and for that we're going to do some Go-I theory. My recommendation for a text on Go-I theory is Cox's book Go-I Theory. There are lots of books on Go-I theory, but I like this one a lot. It does finite fields. It talks about the history. It's all spelled out in what seems to be really, it's not too terse. So anyway, and again, I'm not expecting you. I only expect you to. I'm not going to assign an exercise that requires you to remember some fact from Go-I theory. I might have an exercise where I quote some fact from Go-I theory and then you use it. Okay, but this is the way we do algebraic graph theory. We steal results from algebra and use them. We don't always worry about whether we understand the proof or not. So what's the time? Okay, perfect timing. Yeah, so as I said, we are going to need to do some number theory. Okay, and the right thing there is the machinery we need is stuff related to algebraic integers. An algebraic integer is a root of a mnemonic polynomial with rational coefficients. And so what I'm going to do is I'm going to go through and summarize some of it. Now, some of it stuff we need, we can prove ourselves using machinery, linear algebra machinery already done. There are a couple of steps where it takes more than that. At that point, I just state the result and we get to use it if we need it. But we are not requiring proofs. So I don't have a favorite reference for algebraic number theory anyway. Most of them either are too slow or too fast. But okay, so that's it. That so we do have this. If we have two strongly co-spectral vertices, then we get an orthogonal matrix, which is trying very hard to be a permutation, swapping these things. I will say, if you delete the word strongly, you can prove a similar result, but you won't get the Q as a polynomial in A. So there's a version of this. So I've given you some results about strongly co-spectral vertices, and in many cases there are analogs of these for co-spectral vertices, and you can see those in the notes. I'm focusing on the stuff that we immediately need. I mean, the notes are, of course, in algebraic graph theory and quantum walks, but for this part of the course, I'm trying to focus on the walks. Okay, so there's still the algebraic graph theory coming in. I mean, we just proved that the eigenvalues of a walk regular graph, there can't be too many simple eigenvalues, so there's still algebraic graph theory coming in, but I am trying to focus more on the walks. Okay, and for that, we need information about strongly co-spectral vertices. What I am saying is simply that many of these results are extensions or sharpenings of results about co-spectral vertices. Okay, that's it for today. Any questions?